Huh? Me? What? Oh, in this class on Tuesday, we just kind of chatted a little bit about what the class is going to be about and didn't really do much. Yeah, they carried books for me, too. Okay, here we go. So, fundamental identities. Like I said, an identity in trig is basically one trig expression that is equal to another one. And we're going to start off with some that you guys have seen before. And these are called reciprocal identities. We didn't call them that at the time. Okay, and what is a reciprocal? Just so we can kind of get a head start here. What does it mean? Take a fraction and flip it. Okay, so think about that fact and see if that makes sense for each of these. I'm going to start using a different variable here too. Anybody know what that variable is? What's it called? Theta? Yeah, okay. So we're going to use theta a little more exclusively here with the trigonometry stuff because theta usually refers to an angle. So secant of theta, what did we say secant was equal to? 1 over cosine, okay? So this is one of your reciprocal identities because secant is the reciprocal of cosine, right? You take cosine and you flip it, and that's a secant, okay? So that's one of them. There are 5 more. I bet you guys can probably get them all if you thought about it hard enough, but I'll try and help you out here a little bit. Let's get the 2 more obvious ones here first. What's cosecant? 1 over sine. And then we also had cotangent. And what is cotangent equal to? 1 over tangent, right. All right, so those are 3 of the reciprocal identities. And then there's actually 3 more that people always forget about because we don't usually use these. They're technically true. If secant is the reciprocal of cosine, then it goes the other way too. Cosine's the reciprocal of secant, right? So cosine would be equal to what then? 1 over secant, yeah. And then I bet you can get the other 2 then, right? Sine and tangent both have reciprocal identities. Okay. And those I'm going to expect you guys to have memorized. Okay, there's some of these identities you'll have memorized, some of them you won't, because some of them are a lot more complex than others. But these, I think it's pretty reasonable to assume you can have memorized by the time we're done. Okay? In fact, you could probably memorize them even right now, because you've seen them before. Okay, so we're going to use those in some of our proofs, okay, to simplify things out. We also have what are called quotient identities we're going to use. There's only 2 of these. Anybody tell me what a quotient is? Not a quotation. What's the word quotient mean in math? It's the answer of a division problem, right. And our 2 quotient identities are identities that we use for tangent and cotangent. So what 2 things can I divide and get a tangent? other than the 1 over cotangent that we already talked about. Anybody remember how we would sine over cosine? Remember doing that on your unit circle? Okay. That's actually called a quotient identity. Okay. Now think about this for a second. Tangent and cotangent are reciprocals of each other, right? So if tangent is sine over cosine, what's cotangent? Cosine over sine, the reciprocal of it, right? You just flip it around. Okay, so I want to stop here for just a minute and just mention something, because it's kind of helpful when we get into these proofs later on. No matter what I give you in an expression, be it a secant, cosecant, cotangent, tangent, cosine, sine, do you see how, no matter which of those I give you, you could always write the expression in terms of nothing but cosines and sines? Does that make sense? Every single thing I could give you, you could turn into a cosine and a sine of some sort using these identities. More often than not, that's going to help you to simplify what you have. Doesn't always work, but most of the time it does. And then you can start to cancel cosines and sines and break it down and that sort of thing. And we'll do a little bit of that today. I'll show you how that works. But that's going to be kind of your first line of defense is, can I just get it down to just simply cosines and sines, and then see if anything cancels out, and then check to see what does that leave me with, and can I go any further with it then from there? Okay? And it's going to be mostly these two identities that you're going to be working with, reciprocal identities and quotient identities, to do that, to get yourself started. So, all right, you got a few more identities to get jotted down, and then we'll get into actually like using them and stuff. The last group we're going to look at are called Pythagorean identities. And these, I'm going to show you a little bit more where they come from. Okay, so we're not just going to go right to jotting them down necessarily. Would you think back to your unit circle for just a second? And we'll just look at it in the first quadrant just for simplicity's sake. Okay. So, one of the key ideas that you worked with so that you could evaluate things in a unit circle was that the x value of any point on the unit circle was always the cosine, and the y value of any point on your unit circle was always the sine. So whatever theta was down here, whatever angle you had rotated on your unit circle, to find the coordinates of the point on the circle, it was always the cosine of that angle, comma, the sine of that angle. Does that make sense? You guys all remember doing that? Okay. So this picture kind of demonstrates that for you. Okay, whatever that angle is down there, it's the cosine, and then the sine gives you the x and the y of that point. Okay. Well, I'm going to expand on that just a little bit here. Think about this as a right triangle. Okay, so just focus on this right triangle here. And if this is a unit circle, what's the length of the hypotenuse? 1. Okay, so that's 1. What's the length of the base of this triangle? Cosine theta, right? If that's the x-coordinate, it's got to be how long this is. So this side is cosine theta. And then what's the height of the triangle? Sine theta. Okay, keep in mind, and we're talking about Pythagorean identities, right? Pythagorean theorem works with what kind of triangles? Right triangles, right? Which is what we have right here. And it was that a squared plus b squared equals c squared. Okay, well now I don't have a, b, c, I have cosine theta, sine theta, and 1. So if I use that idea, I can make a new equation using this stuff. So cosine of theta squared plus sine of theta squared equals 1 squared. Right from that little right triangle we just drew. Now I'm going to introduce to you probably a notation I'm not sure you've seen before, but instead of writing cosine theta squared like this, you can write it like that. It's the same thing. Okay, and that confuses a lot of people, and for good reason, because the square is in kind of a funny place. It doesn't look like you're squaring the whole thing, but it just eliminates the need for parentheses if you write it like this. So just know this is one and the same, and then we could do that same kind of idea with the sine, like that. And then 1 squared is just 1, so we don't need to square that anymore. We can just make it a 1. And then that is your first Pythagorean identity. Cosine squared theta plus sine squared theta equals 1. It's kind of an interesting concept. No matter what the angle is, if you do the cosine of it and the sine of it, square them both and add them, no matter what, it always equals 1. And we just proved it using this right triangle over here. So that's going to become an important identity down the road, not just in this section of this class or whatever, but into AP Calculus we use this one quite a bit too. Now there are 2 more Pythagorean identities, but the other 2 we can get from this one. Okay? Remember that you can do anything you want to an equation as long as you do the same thing to both sides. Okay? So I'm going to start with this equation that I know is a true statement that I just proved. And I'm going to divide everything by the same thing. So I'm going to divide both the left and right hand sides of that equation by cosine squared. As long as I do it to every single term, I'm keeping this equation balanced. I'm doing the same thing to both sides. Okay? So all I got to do now is use some of those identities we already talked about up top and see if I can like simplify this out a little bit, write it in a way that's a little bit more cohesive. So what is cosine squared divided by cosine squared? 1, okay. And then what is sine squared divided by cosine squared? Tangent squared, right? Sine over cosine is tangent, so sine squared divided by cosine squared is tangent squared. So 1 plus tangent squared theta equals, what's 1 over cosine squared? Secant squared, right? Because 1 over cosine is secant, so that means that 1 over cosine squared would be secant squared. And so here's another Pythagorean identity. Not used quite so often, but still valid. 1 plus tangent squared equals secant squared. All right, and I would like you guys to give me one more, and I want you to do this one on your own. One more Pythagorean identity. What do you suppose you're going to do this time? Do what? Exactly. Yeah, you're going to do the same process you just did, except now you're going to divide by sine squared instead of cosine squared. See what you get. And that'll be your last one. I'll give you guys a few minutes to take care of that. All right, anybody need more time on that? All right, so should have something that looks like that. Cotangent squared plus 1 equals cosecant squared. Are we good? Yep. Okay. So, with the time we got left, we're going to practice simplifying a little bit with some of this stuff. Okay? I'm going to hold off on the Pythagorean identity stuff for just a little bit because that can be a little bit more challenging. But the reciprocal and the quotient identity stuff, I think we can get right to. So, no, we're not doing an assignment yet. I'm just going to practice together for a little bit. Before we actually start doing proofs, we're going to simplify. Okay? So try to get things to cancel, break it down as far as it'll go, and not worry about actually like explaining all of our steps and what we're doing and that sort of thing. So you're going to see a lot of questions that have this as a direction. Simplify. So let's say like secant theta cosine theta plus sine theta. Something kind of like that. So it's not an equation, right? It's an expression. You guys know the difference between an equation and an expression? Right. An equation has an equal sign somewhere in it. An expression is just some math stuff out there that it's not necessarily equal to anything, but it's just there. So we want to take this expression, secant cosine plus sine, and see if we can break it down so that it is something simpler, okay? Something that's equivalent to what we have here. Still, it would come out the same, but just written in a way that's easier to read, okay? So the first thing that we would do is go through this thing and look to see, are there any identities that we could insert somehow in here to help us out with that? Josh? Correct. So that would be where we want to start with this one then. So 1 over cosine times cosine plus sine. So like I was saying earlier, try to get it with all cosines and sines to begin with, which is what we did here. Just took the secant and rewrote it as what we knew it was equal to, 1 over cosine. And what do you notice now? What can we do? We can do a little canceling there, right? So what's going to be our final answer? 1 plus sine. Be careful that you don't slip into the trap of just saying, oh, it's sine. It's 1 plus sine, right? Because 1 over cosine times cosine is 1. It's not 0. So we end up with, 1 plus sine. And there's nothing else I can do with that, right? That's as far as I can simplify that. There's no other cancellations that are going to happen. So that would be my answer then, 1 plus sine. Okay, so that one was pretty easy. So let's ramp it up just a little bit. Okay, so still have these identities kind of at the ready, but I'm going to make an expression that's got just a little bit more going on here. All right, let's try that expression. Cotangent sine cosine plus tangent cosine sine. So, what do you think? What identities should I use to get this thing started? Yeah. All right, good. Yep, take the cotangent and the tangent, make them into sines and cosines. What kind of identities am I going to use to do that? Quotient. quotient. Yeah, not reciprocal this time, right? So cotangent, take a look at your quotient identities. What is cotangent? Cosine over sine. Okay. And then what's tangent? Sine over cosine, right? Okay. Everybody see what we can do next then? Yeah, go ahead, Jess.
For the one that uses cotangent,
Okay. All right. So we'd have cosine theta times cosine theta over here. Somebody else? What about the other set of terms there? What's going to happen on that one? Right, those cosines will cancel. So we've got sine theta times sine theta. So now what? Yeah. It cancels to 1, right? Because cosine times cosine is technically cosine squared, right? And sine times sine is sine squared. So this whole thing, it is like this is equal, it all comes out to 1. So that big old long expression up at the top is 1 once you cancel everything out. Yep. All right, I'm going to give you guys a few to work on your own. See how you do without me helping you. And then we'll see where we're at. Oh, sorry. This needed to be a cotangent. All right, give those two a try. Put some fraction work in there for you. See if you can handle it. Bless you. All right, does anybody need more time with these? A little bit. The fraction part of it makes it a little bit different. Number one, there's some special kind of cancellation you can do that maybe you're not used to. That might be why that one's creating some problems. And the second one, you have to think about, like, when you're adding fractions together, what do you have to have? A common denominator. So even with trig, we got to search for a common denominator and do that. So cotangent is a cosine over sine, right? So that automatically gives you a common denominator, and then it's just a matter of putting those two together. Now when you're done, it may not look terribly more simplified than what it was when it started with that one, but in the simplification process, technically that's one goal that we would have, is if we have more than one fraction added together, to try and pull that together into one. Because typically if you can take it any further, that's the only way you're going to find it. So I'll show you what I have for both of these real quick, and then we can kind of discuss as needed. And then I think we're good for today. We'll call her good. All right, so here's my first one. Things got kind of tiny here a little bit. All right, so what I did was I immediately turned all four of these into what their identities say they are. So cosecant and secant, I use the quotient identities. Cotangent and tangent, I use the secant and cosecant, I use the reciprocal identities. Cotangent and tangent, I use the quotient identities. And I got this. So are we all okay there at least? So yeah, they have all those like crazy fractions in the fractions and everything. Okay. If you take a look, these two right here, do you see how those are both fractions that are over sign? If I have a fraction over sign divided by another fraction that is with sign on the bottom, I can cancel those two denominators out. Okay? And here's why. If I were to take this, you guys remember the whole leave it, change it, flip it business with fractions? That if you take whatever you're dividing by, you can flip it, you can take its reciprocal, bring it up and multiply. Okay? Take the reciprocal and multiply should be what you're saying. Anyway, if I were to take this fraction and make it sine over cosine and multiply it, do you see how the signs would cancel then? That's really what I'm doing, is I'm canceling those signs. I'm just doing it before I even do that process. Okay? And it's just something that you have to get used to after a while. If you see a fraction divided by a fraction and they have the same denominator, just get rid of them. Okay? So this becomes just 1 over cosine. And the same thing happens over here with the cosines. The cosines cancel, and it's just 1 over sine. And 1 over cosine is secant, and 1 over sine is cosecant. So it's the secant plus a cosecant. Okay? So does that process make sense now that I've shown it to you? Okay. All right. And then this second one, like I said, your answer might not seem simplified, but it is. It's over sine, right, both of them. So what do you do when you have two fractions with common denominators? You add the numerators, put it over the common denominator. Cosine squared plus cosine over sine. Now you can factor, I guess, technically a cosine out of the top if you wanted. So it'd be cosine times cosine plus 1 over sine. But it's kind of all the same at that point. Yeah?
Could you change that to cotangent theta plus cosine squared theta?
Where at? Right here?
Yeah, because we have
Exactly. Yeah, they're both divided by the sign. So, any questions on number 2 otherwise? Yeah.
Will we ever get like cosine to the third theta?
Possibly. We're going to talk, actually tomorrow it's going to be kind of our focus is dealing with ones that are a little bit more complicated like that, where we're going to have to introduce some new strategies like factoring we might need to do. Like for something like that, if you have a cosine to the third, and you might need to factor out a cosine so it leaves you with a cosine squared so you can then use a Pythagorean identity. So tomorrow our focus is going to be Pythagorean identities and factoring, really. And then mixing that in with these kind too. All right. So, but for today, I'm good if you guys want to be done because we did a lot already. Okay, I think we're good to go. All right, so here's where we're going to start today. We're going to simplify this expression. Yesterday I talked about how it's always a good strategy to try and write an expression all in terms of sines and cosines, if possible. And sometimes you're presented with one that's already there. And it might seem like you don't have really anywhere you can go with it. But one option that you should try, if you don't have anything else, is factoring. Because sometimes when you factor out a GCF, that presents something that looks familiar that you might be able to use then. So in this particular one, we can do a little bit of factoring. What do you guys notice? What could we factor out? Sine x, right? So if we do that, then what's going to be left behind? So we get a sine squared x when we take out a sine out of this first term. And then in the second term, we get plus the cosine squared x. So, what do you notice? See another identity in there that we talked about yesterday? Sine squared plus cosine squared, we said, is equal to 1. So, this entire expression is actually equal to what then? Just sine x, right? Okay, so sometimes, like I said, factoring is going to open up something for you like that one. There are other times when applying things back together is going to be helpful. So, I'll give you an example of that. And these, you kind of just have to get used to them a little bit, because there's a real temptation here to just take it and say, oh, I see some secants in there, and I'm going to turn those into 1 over cosine, because that's what Mr. Herrick said to do, and then you're going to get stuck, and nothing's going to work. So, anytime you see two expressions multiplied together, or that are next to each other being multiplied, where the only difference is like a plus on one and a minus in the other, you're going to want to multiply those together. Okay? Because the result of that is going to set up a Pythagorean identity potentially. Okay? So, you guys all remember differences of squares? And factoring differences of squares? Well, if we multiply those back together, okay, is what we have here at the top. What is that going to give us? If we do sine x, or secant x plus 1 and secant x minus 1, what is that all multiplied together then? Okay, because those two middle terms are going to cancel each other out, right? 1 times secant x and negative 1 times secant x. Those will cancel, and then it's just secant squared x minus 1. And that divided by sine squared x. So, can anybody see the Pythagorean identity we're going to use here? This one's a little tricky. Take a look at the Pythagorean identities we wrote down yesterday just for a second. Do you see one we might be able to use? If you think you got one, raise your hand and we'll jot it down next to the problem here and see if we can make use of it somehow. Yep. Mm-hmm. Now the common misconception here is that I can only use this Pythagorean identity if I see a 1 plus tangent squared somewhere. And that's not the case. It's an equation. I can manipulate this thing however I want to, right? So if 1 plus tangent squared x is equal to secant squared x, equivalently, secant squared x minus 1 equals tangent squared x, right? So really, anytime I see a secant squared minus 1, I can also use this identity. Okay, so what does that mean for our problem over here then? How am I going to continue to simplify this thing? Right, I can do a substitution, take that secant squared minus 1, turn it into a tangent squared. So now I'm looking at tangent squared x over sine squared x, which is already much simpler from what we started with. Now at this stage, I can take that tangent, break it down into its cosines and sines, see if we got anything that's going to cancel out there. Okay? So tangent is sine over cosine, right? So we've got sine squared x over cosine squared x, and that whole thing divided by a sine squared x. Whoops, like that. So what can I do with that? I got a fraction divided by sine squared. So back to our kind of fraction talk we did yesterday here a little bit. How can I manipulate this thing to get it to simplify some more? So it's multiply like both the top and the bottom by sine squared x, that sort of thing? That actually wouldn't help, because then I'd end up with a sine to the fourth x on the bottom and on the top. Think about it this way, dividing... Oh, go ahead.
Since we're dividing the fraction by a whole number, wouldn't we turn the sine squared of x, or wouldn't we use the reciprocal of it to multiply it?
Mm-hmm. Yeah, exactly. So we would have sine squared x over cosine squared x, and then instead of dividing, we multiply, but we got to multiply by its reciprocal. So it'd be multiplied by 1 over sine squared x then. And what's going to happen then if we do that? You can do some cancellation there, right? Those sine squareds will go away, and we're going to be left with a 1 over cosine squared. And what is 1 over cosine squared? Secant squared. So this one simplifies all the way down to a secant squared from the beginning. All right. So, yeah, it is a little tricky because sometimes you got to factor. Sometimes you got to multiply things together. Okay? You just kind of have to look at the problem and see what kind of presents itself that way. All right, the factoring, if you have multiple terms to begin with, and you can see a GCF in there that you could pull out, try it. It might work, it might not. If it does, great, then you can keep going. Other times, if you see two binomials, like in this case, multiplied next to each other where they got opposite signs, usually that's going to be a place where you multiply it together, then use a Pythagorean identity somehow to keep going from there. You just got to get used to seeing those and recognizing that as you go. Okay. Let's do a little bit of solving with this stuff. I should have put this on the board, but I didn't. Sorry. Same idea, but solving equations by using some of these identities. Okay, so we're going to look at that. So we've got 2 cosine x sine x minus cosine x equals 0. And then I want to solve on the domain 0 to 2 pi. Because like we found doing trig stuff back in chapter 4, that if I don't give you a domain to work with, there's infinite answers you could have for this. You keep going around your unit circle and you'll keep hitting different places, or keep hitting the same place again and again and again and again, and you get all these solutions. So we're just going to go 0 to 2 pi, just keep it on the unit circle one time around. But the equation we're solving this time is a little bit more complicated than the stuff we've done in the past. So let's think about some of the things we've talked about in simplifying expressions. See, is there a way we could simplify this maybe somehow to help us out? Okay, so what do you guys think? We got 2 cosine x sine x minus cosine x. Yeah. Okay, do a little factoring here to get started. That's a good idea. So if we take out the cosine, we end up with that. Now, are there any identities that are going to help us to break this down any further? Yep.
Never mind.
Okay. So any identities that are going to help us? Yeah? Sure.
The power function to the sine squared.
Do sine, how, what do you mean by power function?
What do you do with the log? That 2.
Oh, no. You can't. I hear what you're saying. You can't bring the 2 up. Yeah. Only with logarithms you can do that. Yep. Okay. So, yeah?
You do the zero factor theorem, because cosine x equals 0 and 2 sine x minus 1 equals 0.
Right. Yeah, you can't do any identities here any further. But you do have technically 2 things multiplied together that equal 0, right? So you could do the zero product property, which says one of those 2 things that you're multiplying together has to equal 0. So either cosine x is equal to 0, or this 2 sine x minus 1 is equal to 0. And then you got to try and solve each one of those individually. And here's where our unit circle is going to come back into play again. So think unit circle, where is the cosine equal to 0? What angles make the cosine 0 on your unit circle? That's right. X equals pi over 2, and x equals 3 pi over 2. The top and the bottom of the circle is where cosine is 0. All right, and those are the only 2 I need, right? Because I'm only solving in between 0 and 2 pi. Now, this other one, they've got a little bit of work left to go on that one, right? Yes, sir?
Wait, how do you know one of those equals 0?
How do I know the equals 0?
Yeah.
Because I've got a multiplication of 2 things equaling 0. So one of the 2 of them has to be 0 to make that come out to 0. So what about that second one? 2 sine x minus 1 equals 0. So, Jack? Right. We got to do a little bit of work here. If we add the 1 and then divide by 2, sine x has got to equal a half. Okay? But that's all right, because 1/2 is a value that's on your unit circle still, right? So we can think about that. Okay, so where on the unit circle is the sine equal to 1/2? Okay? So x equals pi over 6 works, but not 11 pi over 6. 5 pi over 6 is the other one. Did you catch your mistake there? Yeah. All right. So these would be our 4 solutions to that equation then. And 5 pi over 6, all of those will make that equation equal 0 if you plug them in. Okay. So sometimes when you're doing this stuff, you're going to do some identity work in the middle there too to simplify it up for you to help out. Sometimes you don't need to, like this one. Almost always, though, it's going to involve some kind of factoring to get it started at least, because you're going to want to use that zero product property. Okay. This one was already set equal to 0. If it wasn't set equal to 0, then that's going to be your first step. Get everything off to one side, 0 on the other, look to factor, and then try and set that 0 product property up like we did on this one, and go from there. Okay? All right, before I let you jump into homework, there were a few other identities that I wanted you to take a look at. Now, you don't necessarily have to write these down into your notes. These are not ones that I'm going to make you guys memorize, okay? But they are other ones that will come into play. And in the past, I've done like a proof of why they work and all of that, and it just took a ton of time, and I didn't feel like it was really worth it at the end of the day, so I'm just going to show them to you. If you are curious about them and where they come from, I will show you later. That's fine. I don't mind it. I didn't take up class time to do that. But if you look on page 447, that's where I'm getting these from. Okay, or you can just look up here, I suppose, because they're right here. But we've got this set of identities that are called co-function identities. What's the prefix co mean? Together, okay? So like cooperation, that sort of thing, you're working together. Okay, so there's these functions that kind of go together. Sine and cosine kind of go together, okay? So sine of pi over 2 minus theta is equal to cosine, and then the flip of that, cosine of pi over 2 minus theta equals sine. That one I can kind of quickly describe. Think about a right triangle, okay? The two angles, the two acute angles in a right triangle always have to add up to what? 90 degrees, right? Or in the radian world, pi over 2, right? So, does it make sense that the sine of one is just 90 degrees, pi over 2, minus the angle, gives you the other one? Think about doing that in a right triangle, right? The little ratio that you would get would be the same if you just subtracted it from 90. So, sine and cosine work that way. And it just so happens that all the other trig functions, that same relationship is there too. So tangent and cotangent have this little 90 degrees or pi over 2 difference, and secant and cosecant do as well. Okay? So if you want to jot these in your notes, by all means, but it's in your book on page 447. They will always be there. And I won't make you memorize them for your test or your quest coming up next week. So just so you know, though, some of your homework problems, throw some of those at you too. They're pretty easy to recognize. As soon as you see pi over 2 minus theta, cofunction identity, and you can just replace it real quick. The other set on here are the odd-even identities. And these come about more from what the graphs of these things look like. So if it's an odd function versus an even function, they have different relationships. And students always get these confused, so that's why I stopped having people memorize them. But sine of negative x is equal to negative sine x. Cosecant of negative x is negative cosecant x. Those are odd functions. That's why those work that way. Cosine and secant are even. So cosine of negative x is cosine of x. Secant of negative x is secant x. That works because those are even. Tangent and cotangent are both odd. So tangent of negative x is negative tangent x, and cotangent negative x is negative cotangent x. Okay. Again, I can show you the graphs and explain if you want, but it's just, no, that's why. And again, these might be in some of your homework problems, but they're pretty easy to recognize, right? As soon as you see a sine, cosine, tangent, secant, whatever, of negative x, then just replace it with the other, okay, from this little list. So, all right, just wanted to at least for a loop later on. So, okay, I'm going to let you guys get started on your homework here, doing a little simplifying, a little bit of solving in the mix there too. And you got some time, so let me know if you got any questions.